Okay, so we are starting with the applications of natural language processing, and the first application which we are looking at is information retrieval. What is information retrieval? It is basically getting information from some repository. Okay, say for example, what we do in Google search is we give a query and we the system actually searches through a repository of documents and gives the relevant documents in return. So that is an example of information retrieval. Okay. So more formally, information retrieval is storage and retrieval of all types of media. Here we are only talking about text as input and text is the output, but it could be give an image as input and get an image as output. So it involves both the storage and retrieval of different types of media. And speaking in a formal way, we will look at the terminologies involved. So what is a document? It is the unit of text indexed in the system and available for retrieval. That is the unit of information retrieval which we talk about. So every document is indexed and identified. Any identifiable unit is called a document, and collection is a set of documents, and the term is a lexical item. Okay, a single item is known as a term, and a query consists of query which is users information. Information need is expressed as a set of terms. Okay, in Google search also we type a set of terms and we get a set of documents as a response, right? Now how is this happening and what happens under the hood? Okay, so that is what we are going to look at. Now this is the input part. You have a query. The user has a query, and the query has to be processed in some way. Maybe some irrelevant items has to be removed, like say comma or spaces or something has to be removed, and it is being given to the actual repository. We said the repository is a set of documents which has been indexed in some way, and there the query is searched in these documents. The search happens, and the output is a set of ranked documents. And how is the search done? There are different ways. One sort of way in which all this can be organized is called a vector space model, which we will be looking at. Okay, so what is a vector space model? So we said we have a set of words as the input. We have several documents which are stored, and as output again we have a set of ranked documents. So how can how can any sort of processing which has to be done inside a computer, you have to have it represented in terms of numbers, right? Here we are talking about text. So how can we actually build a model based on this text? What sort of model and search happens inside or in the back end part? Okay, so it is explained using the vector space model. So how the queries as well as how the documents are organized is using this model. Okay, so in the vector space model of information retrieval, documents and queries are represented as a set of vectors of features representing the terms that occur within them. So again, a vector means you can represent this. This is an example of a vector. Okay, vector means you can have several dimensions. You can have numbers in several dimensions. So xy coordinates we represent on a graph xy coordinate. That is a vector of 2 dimensions. Here we have got a 4-dimensional vector. So any query or any document is represented as a vector. And vector of features. Okay, these dimensions are also known as features. People who have a little bit familiar with machine learning will know about the concept of features. Basically, these dimensions are called features. So any vector, any query or any document, anything is represented as a vector in the vector space model. Okay, so they are represented as vectors of features consisting of terms that occur within the collection, with the value of each feature indicating the presence or absence of a given term in the document. So let us say we are again searching for our query is again vector space model. That is our query. Okay, so how can you represent that query in terms of a vector? How can you do that? Okay, so how take the pen. Okay, let us say my system, my vector space model has 10 words only, and I am representing vectors. So first dimension says whether vector as a word is present in our query or not. So you can represent it using a 1. Next, let us say is some other word like say chicken. So it is not present in our query. So you represent it as 0. And next is, let us say, space. So it is present. Next is recipe. So it is not present. And model is present. Maybe oil is not present. So these are basically, so we are assuming there are some set of words which are accepted by a model, and then we can represent it either like this, that is whether a word is present or not, or maybe each of these features can represent how many times, so the frequency of occurrence of the words can also be one way of representing it. Basically, our document as well as our vector query is represented as a vector like this. Okay. So the queries and documents are represented as vectors of features consisting of the terms that occur within the collection with the value of each feature indicating the, okay, here it is presence or absence of the given term in a given document. That is how, and it is also known as a bag of words representation. So you have a vector bag of words. Okay, that is one representation of. So you have a set of words and you indicate whether it is present or not. The value of each feature is called a term weight. Okay, here it is either 1 or 0, and it is a function of the term frequency in the document. Okay, you can also have it as a frequency. Here we said it is a presence or absence of a term, but we can also say it is a number of times. So that is what is represented here. It is a frequency of occurrence of that term in the document. Say for example, a document which has fried chicken recipe, there are only 4 terms and it occurs, chicken occupies 8 times, fried twice, oil 7 and pepper 4. So this is one way of representing this particular document using a vector space model. Okay, so more generally speaking, a vector for document dj can be represented as a vector like this with multiple weights w1j, w2j, w3j up to wng, and this n, which is the dimension, it actually is the maximum number of words which is recognized by our system. Okay. So similarly, a query can also be represented using a vector. So Q, a query, fried chicken, is represented like this. That is, fried and chicken are present one time. Now, the dimension n of the vector is the number of terms in the whole collection. Okay, so that is how we said our vector is of size n, and n is the number of terms which are recognized by our system. The features corresponding to queries or documents can be thought of as possible, okay, in a multi-dimensional space. So we are talking about vectors. So if you are drawing it on a graph, each of these vectors can actually be represented as points in a multi. Here it is 4-dimensional, but you can think of these as points in space. Okay, here it is 4-dimensional space. So the features corresponding to the queries or documents can be thought of as points in a multi-dimensional space. And documents that are close to each other in space are similar to each other. So this is a point, and or you can say from the origin you can think of this as a vector, right? You can think of this as a vector like this. And if you have two vectors which are close to each other, which means they are very similar, or the words in it are actually close to each other. So if they are close to each other means you can think of it in terms of the angle between them, right? So generally similarity between vectors can be represented using what is known as cosine similarity. I think we have come across it earlier also. Um, okay, this is an example. You have this query fried chicken is a point here, and this is a vector, and the document fried chicken recipe is here, but poached chicken recipe is somewhere here. So we can see that this query fried chicken is actually closer to fried chicken recipe than poached chicken recipe because they're more similar. So you can think of it as an angle can be used to represent how close each of these points are in space or vectors are in space. Okay, so since we're talking about cosine similarity, we're talking about mm, vectors and the angle between them. So we can say this is the standard method for representing cosine similarity. Now, cosine similarity, I think we saw it once. If we talk about two vectors, say A and B, okay, two vectors A and B uh, of some n dimensions. So you can say A dot B is equal to, say, A has n dimensions, right? A1 into B1 plus A2, B2 plus etc. A and B, and you can write, right? Etc. A and B. You can write it like this. Now, A dot B is, you can also write it as absolute value of A into absolute value of B into cos theta. Okay. So so equating these two, you can say cos theta is equal to, you can say sigma AI BI divided by absolute value of A means square root of AI squared, sigma AI squared into, okay, square root of sigma BI squared. Okay. So cos theta is this, right? So here we said theta is the similarity between two vectors. So if two vectors are actually the same, the angle is 0, then you have maximum similarity because cos 0 is 1. And when they are at maximum distance, cos 90 is 0, then similarity is 0, right? So it is the same representation is being used here. So similarity between a query as a vector and a document as a vector, you can write it as, so we said the query as well as a document. Query is represented as WIQ. The query is weight. Weight, we said, either the presence or absence of a feature or the number of times that a particular feature occurs, right? So look, it is AIBI. Instead of that, you are saying WIQ into WIJ divided by sigma WIQ squared. So this is the same concept is being used here. This is known as cosine similarity. So cosine similarity can be used to find out the distance between a query, an input query, and the document. So we said we have many documents, index documents in our information retrieval system, and the system, say maybe Google actually, in Google we give a particular query as input. So you want to find out, okay, the documents which are most relevant. So for relevance here we are using cosine similarity. So between each query which is represented as a vector and the document which is again represented as a vector, you find the cosine similarity between the query and all the documents which are present inside our system, and then we rank them based on the cosine similarity. That is what we do. So in a document retrieval system, the query is compared with all the documents and rank based on the similarity measure. So that is how the simplest way of representing or explaining information retrieval is like this. Okay, term by document metrics. The documents can be represented as a vector of term weights, or here, if you look at it, the columns represent the document. Okay, documents, all the documents together can be represented as a single matrix if we want. Okay, columns represent documents and rows represent the particular term. This is one way of representing it. This is not really mandatory. Okay, next we come to the concept of term weighting. How is a term being represented in our system? So earlier we said we can have a bag of words model where every word we represent it either as present or not, or a little more better model is what is the frequency of occurrence of a word within a document. That is another way of representing it. Now, so that is the simplest way. So term weights can be simple frequency counts. Okay, intuition that terms that occur frequently reflect the meaning of the document. That is why we have frequency count for using or representing the documents. That is, terms that occur frequently reflect the meaning of the document. But there is one slight problem with this representation. There are many words like and, the, and so on, and there are many frequently used words which might occur very frequently in all documents but does not convey such much meaning. So, do we have an alternate way of representing these terms? Okay. So, another factor can also be considered in representing these terms. That is, we can give higher weights to terms that occur only in a few documents. Okay. So instead of just counting the frequency of occurrence of words in documents, in order to discriminate between documents, okay, in order to discriminate between documents, can we find out those words which are occurring only in a certain document? That provides more discriminative power. Okay. Okay, so these terms are useful in discriminating between documents. Terms that occur frequently across documents are not useful because if we are using terms which are there in all the documents, then you cannot discriminate between document and find out which one is the most relevant. Right. So if you are able to find words which are present only in, say, one document, say chicken fried rice, that will be present only in documents which talks about, say, the recipe or something like that. It wouldn't be present in, say, a movie review. Let us say another document. Right. It is a discriminating word. Can we find out discriminating words? So we come to what is known as along with the frequency count, and we have some discriminating words also. So that is where we have the concept of inverse document frequency. Okay, inverse document frequency means assign higher weights to more discriminative words. Now, how can we do that? How can we represent that? So that is represented as, so inverse document frequency is represented as n by ni, where n is the total number of documents which are there, and ni is the number of documents in which some term I occurs. So we are trying to find out discriminating words. So discriminating words means those words might not occur in all the documents, but it will be present only in the relevant documents. So if this particular term or this particular what terminology is used in order to find out IDF. So it is n is a total number of documents divided by number of documents in which term I occurs. Now, when you have fewer the documents in which I occurs, higher the IDF value. So, when you have discriminating words, will have IDF as a higher value. Okay. So, here what we are doing is we are trying to find an optimal measure in order to find out words which are frequently occurring but also providing more discriminating power to it. Okay, so what we can do is we can combine the frequency as well as inverse document frequency. Now, before taking the weightage, inverse document frequency we said is represented using n by ni, but since the number of documents, since say let us say we are talking about Google search, there will be millions of documents, right? So instead of taking n by ni, we are also taking a log in order to actually squash the value. That is, in order to have a smaller value. Uh, so for that, we are using log. Okay. So here, so for weighting a term, we are also using term frequency. That is a frequency of the number of times the word occurs, as well as the IDF. That is inverse document frequency in order to provide discriminating. So the weight or the term weight we're talking about is term frequency inverse document frequency, or it is generally referred to as TF-IDF. Okay, so based on TF-IDF, you can also same similarity measure which we saw with TF-IDF substituted is given here. Okay, that can be used for finding the similarity between query and the documents. Okay, this is about what are the terms selected. Okay, all words in the documents are not considered, and two methods are used in order to filter out the words which are selected for representing the representing as part of the vector. So first step done is stemming. Stemming is a process of collapsing together morphological variants of a word. Say, for example, process, processed, and processing can be combined to or reduced to a single word called process. Otherwise, if you have if each of these are represented as three different values, then your discriminating power will be lesser. Okay, so stemming is a process of reducing the three representations to a single representation. Then you have another concept called stop word removal. Say for example, the is actually a word which is occurring everywhere, but it doesn't provide any discriminating purpose. Such words are called stop words. So before actually going in for information retrieval, we have to select the terms which have to be used for representing the query as well as a document. So that is called term selection. And for term selection, first we have to do stemming as well as stop word removal. Only after that we find out the words which are to be used as the vector. Okay. Okay. So here we have talked about information retrieval. Information retrieval. First thing is we do a stop word removal and a stemming process, and then you identify the terms which are involved, and these queries and documents are represented in terms of a vector, and both queries and documents are represented as vectors. And in order to process a query, what you do is you find the similarity of this query to all the documents stored in your system, and then you rank it based on the similarity value. So that is how information retrieval works. Now, how can we evaluate information retrieval systems? Okay. Generally, when we these are terms which are very common in machine learning systems. Uh, in general machine learning systems, to find out whether our system is working properly or not, we might need some sort of a measure to identify whether our information retrieval system or a machine learning system is working as we are expecting. Okay, according to our expectations, whether it is working properly. So we need some sort of measures. So precision and recall are two measures that are commonly used in machine learning systems. Now we look at what are these, and then we'll move on to some measures just specific to information retrieval systems. Okay. So to find out whether a retrieved document is relevant or not. So we said we are ranking in information retrieval. What we do is we retrieve the documents which are most relevant to us, and we rank it based on the relevance. That is what we said. So are those documents which are generated, or is the output generated by your information retrieval system, whether it is actually relevant or not? If we are claiming it is relevant, so we have to measure whether it is relevant or not. So how can we do that? So retrieved items can be grouped into either relevant or non-relevant. So you can classify it. So it's basically grouped into classified into relevant and non-relevant. So we can use measures like precision and recall measures, which are generally used in classification systems or machine learning systems, in order to measure whether our system is working correctly or not. Now, let T be the set of documents that are retrieved as a result of a query. Okay, we have say T number of documents, 1, 2, 3, etc. T documents are retrieved as a result of a query. Now, R of them are relevant. Okay, R of them are relevant documents, and U is a set of all documents in the collections that are relevant to this query. Okay, now, so T is the total number of documents which are retrieved by a system, out of which R is the relevant set. So precision we define is out of the total number of systems which are retrieved by our system, how many of them are relevant? Out of the total number of systems retrieved, how many are relevant? That is what precision is. Now, recall is out of the total number of relevant documents which are present in the system, how many have been retrieved by our system? Okay, so precision is out of the total number of documents retrieved as relevant by our system, how many are actually relevant? And recall is out of the total number of systems, out of the total number of relevant documents you in the system, how many have been retrieved? Okay, so these are two measures which can be used to find whether our system is working perfectly or not. Some mathematical measure. Okay, so this so far it is okay, but the problem is these two measures is this is generic machine learning or classification system based measures, and here we are only looking at how many have been retrieved. We are not looking at what is a sort of ranking. We are not looking at the rank at all. So information retrieval, we know that we only look at the top ranked documents which have been retrieved. So if those top ranked ones are not relevant and the lower ones are relevant, then the user will not look at those things at all, right? So the ranking is important. So can we incorporate that ranking also into our evaluation measure? So we will look at two more such measures which also incorporates the ranking into the evaluation of the information retrieval system. So two things are considered. One is 11-point precision recall curve and the other is mean average precision. Okay, so in order to understand what this 11-point precision recall curve is, so we let us say we have documents 1, 2, 3, 4, like this. We have documents retrieved by our system. Let us. Okay, now in 11-point precision recall, or we here what we are trying to do is we are trying to plot precision versus recall. Okay, for every document which has been retrieved. Not like in the case of previously, we were talking about precision and recall separately. Then we said out of the total number of documents which have been retrieved, how many are actually relevant. So it is a totals we were looking at here. Let us say we started document number 1. Okay, we have the 4 documents have been retrieved and we are looking at document number 1, and let us say this is a relevant document. Okay, first document which has been retrieved as a result of a query is a relevant document. Now how do you say what is a precision? Precision is out of the total number of documents retrieved by the system. Now only one has been retrieved, and how many are relevant? So out of one is relevant, right? And so our precision is actually 1 here. Now what about recall? Let us say it is total number of say we have 10 documents, and uh, recall is here out of those 10 documents, one has been correctly retrieved. Okay, so it is 1 by 10, and so it is 1. Okay, so our recall is 0.1, precision is 1. Now we plot it on the curve. Say it is 0.1, maybe it is here. For our point after the first document is actually here. Now we will look at 2. Let us say this is not relevant. Okay, this is 2 is not a relevant document. So what is the precision now? We have seen 2 documents. Out of 2 documents which have been retrieved, 1 is actually relevant. So this is 0.5. Okay. And what about recall? Again, it is 1 out of 10, only 1 is correct, right? So we say this is our, we come to 0.5 as our precision. Recall doesn't change. So we have a curve like this, right? Sorry, this is straight down. Okay. Now, what about the third one? If you are looking at the third one, let us say this is relevant. So our precision becomes 2 by 3, right? Precision becomes recall, 2 by 3, and recall becomes 2 by 10. Okay, 2 by 10 is 0.2, right? So basically from here, the precision actually goes higher. It was 0.5, now it becomes 0.66, and recall also improves slightly. So basically what we have is this. Okay, we'll have a jagged curve like this. Okay, that is you start from here. When you don't retrieve a document, your precision goes down, recall remains same. Recall changes only when you have a new relevant document, right? Okay. Now, next time you have a relevant document, look, the precision goes up, recall also slightly goes up. So you'll have a sawtooth curve, something like this. That is what we get. Now, when you have this precision recall, that is basically what you're trying to do is you plot a precision recall curve for multiple systems. And for ease of comparing, you are actually saying you are using an 11-point precision recall curve. 11 point means at 11 different recall values, you are plotting the precision only for those. Okay, you want to compare two different information retrieval system, and also in order to smooth out these sawtooth curves, for ease of comparison, we are also doing some interpolated precision. Okay, we are doing some interpolation. Interpolation is that is your precision. You are taking, that is the interpolated precision at certain level of recall R is defined as the highest precision found at any recall R. Okay, so instead of having a jagged curve, what we do is for a particular recall value, you actually, so for highest precision, uh, that is a particular recall value, you take the highest precision at that point. So for this particular recall value, highest precision is this. And as the recall moves to a higher value, look, this is the highest uh, uh, precision at this particular recall value. So you actually find the highest precisions at different recall values, and then you try to smooth out this curve. At different recall values, you try to smooth out this curve like this. So that is the interpolated precision we are talking about. Instead of a jagged curve, you take the maximum precision at a single recall value, and you're doing it only for 11 recall values. And what are those recall values? These are the different. For these recall values, you find out what is the highest precision at the particular curve. And that is how you plot this 11-point precision recall curve. Okay. So you'll have a curve like this, which is not as jagged as this. You'll have a curve something like this for us. Okay. At different recall values, what is the highest precision at this point? So you have a curve like this coming up. And for different information retrieval systems, you come up with this, and then you can actually compare. So that is the idea of 11-point precision recall curve. So here we are taking into consideration the ranks also. But again, this is only two different curves which are going to compare. But if we have a single number which can be used for comparison, that will be even better. So that is what mean average precision value is, MAP. Okay, in MEP, what we do is we descend through the rank list of items and note the precision only at those points where a relevant item has been retrieved. Okay, so for you have a list of items, you go through those rank list of items, and we find out the precisions only at those points where we have a relevant item. Okay, now these individual precisions are averaged, and this average value is taken for multiple queries on the system. Okay, so for one query, what you do is you find the precision at various points wherever you have a relevant document retrieved. Okay, and at all those points, say for example, here we said we have 1, 2, 3, 4 are the different queries, and so we'll take precision here because you have a relevant document retrieved and the value is 1. Now we don't take a precision at this point because we do not have a relevant document retrieved, but at 3 we will take a precision value because we have a relevant document. And we take, so here we have one, here we have got 0.66, and we go through this list, and wherever we have a relevant document, we will take the precision value, we take an average of that. And this is repeated for multiple queries which you are giving to the system. And you take an average of that, and that is our MAP. Okay. Okay, so here the precision is computed for k is equal to 1 to mj. That is k is, that is at points where you have relevant documents. That is what this k stands for. And you are taking 1 by m because you're taking an average of those precisions. And q is the multiple queries. You are applying many queries to it. So J is equal to 1 to Q is a multiple queries. For all the queries, you are taking this average precision and then you are taking an average of that. Okay, so that is why it is called mean average precision. So the advantage of this is we are taking into consideration the ranks of the relevant documents, and also after computing the values we get a single number with which we can compare say different information retrieval systems. So that is the advantage.